After seeing this picture, what do you think, feel, and sense? More importantly, how do you think your body can translate those messages to your brain? We'll be talking about neurotransmission, how we send messages to our brain after stimuli, and more importantly, focus on the action potential.
So in this section, we're going to deal about more of the nervous system, which really consists of billions of nerve cells that work together. So we're going to label this part. Now this is a singular cell that is a very basic unit of the nervous system called a neuron. And now the protrusions here are called the dendrites. And this body mass right here is going to be called the cell body. And this long line tube thing is just going to be called, the axon. And notice how there's arrows pointing from my left to the right. So that's basically because these messages are only going to be passed down through that direction.
After a message is sent, there's going to be something called a refractory period, where after the message is sent, there's a period of silence. This is a cross-section of a neuron cell, and on the outside of the cell membrane, we have a huge amount of sodium ions, which are positive. And on the inside of the cell, we have potassium ions. They're also positive, and the potassium ions inside, they don't amount to as much as the sodium ions on the outside. And also, in addition, some of the proteins inside the cell are slightly negative. So the overall charges on the outside, it's a positive, and on the inside, it's a negative charge. And now this kind of mechanism setup is kind of what causes polarization. So this kind of setup is called the resting potential. There's no messages sent at this point, and it is at negative 70 millivolts. This is called the sodium-potassium pump, and it just helps to restore the resting potential by exiting out 3 sodium ions to the outside of the membrane and pumping in 2 positive potassium ions. There's a potassium leak channel, which allows excess potassium to leave the cell so we can have a gradient later on. After you've experienced the stimulus, it triggers up the sodium channels like this purple dot here and makes it open. So now we have more of an influx of sodium ions. So now that the sodium ions are flushing from the outside to the inside of the cell, this builds up voltage so that we hit a membrane or threshold potential that is negative 55 millivolts. Sodium channels open, so this is that red dot here. It opens, and so even more positive sodium ions rush in. Now, through this double influx of sodium ions, we have what's called the positive 40 millivolt range. And this is when the action potential is reached. We hit a stage called depolarization. And remember, we said that on the outside it's going to be more positive than the inside, but now because we have so many positive ions going in, now the internal part of the cell is positive and the outside is negative. So that switch in signs, the switch in currents, is what causes a brief depolarization. So now the action potential will kick off from this area region, and it'll continue throughout the body of the neuron. As you see these dots here, there's so many sodium voltage gated channels, and so this sets off a chain reaction and it'll trigger these proteins so that it'll open up these gates and will allow more of the influx of the sodium ions into the cell.
This flow from my left to right is what kicks off that electrical signal.
Now repolarization comes in. So now we want to turn the inside back to a negative and outside positive again. So we have voltage gated potassium ion channels that are now activated, and they let out the inside positive potassium ions, and they let that out to rebalance the charges. Now hyperpolarization comes in. Now the voltage is dropped to negative 75 millivolts because of this let out of the potassium ions before all the gates close. And then the sodium-potassium pumps, the coffee bean here, takes over, and the leak channels here, they take over to rebalance everything to negative 70 millivolts.
Saltatory conduction, saltatory means to jump, and usually the action potentials just go and jump like this, and this makes the action potentials travel a lot faster. They jump over these magenta things called myelin sheaths, and the spaces between them are called the nodes of Ranvier. It just really goes by quick, like 1 to 100 real fast. And, this process is pretty lit. So, action potentials
are all of the same strength. However, a weak stimulus and a strong stimulus, the difference between that is that the frequency of the action potentials make something more intense than the other.